morning. It's my greatest pleasure to introduce today's speaker, Dr. Xiaodong He from Microsoft Research. Xiaodong got his PhD from University of Missouri in 2003. After that, he has been working in the area of machine translation, information retrieving, speech recognition area. One of the most impressive accomplishments in that group is they got this Chinese to English translation competition in terms of performance evaluation in 2008, NIST competition, and also 2011, another international conference competition. And Xiaodong is currently also the associate editor for IEEE Signal Processing Data and also Signal Processing Magazine. So let's welcome Xiaodong for his wonderful talk.
So thanks, Professor Huang, for the very nice introduction. It's my great pleasure to come here and today, and I want to share with you some exciting progress in a relatively new technology called deep learning. So deep learning has demonstrated great power in several key artificial intelligence tasks like speech recognition, image recognition, and it's going to actually quickly change the landscape of artificial intelligence. So today, actually, I'm going to focus on how to apply deep learning to several key natural language processing tasks, which actually will infect our daily life, actually. So this is a work, and this material presented in this talk is based on the collaboration and discussion and many exchange communications with my collaborators like Jianfeng, Li, and many others. So first, a little bit of background about deep learning. So nowadays, everybody probably hear about machine learning a lot. So by machine learning, we basically mean you collect a lot of data, then you compute the statistics from the data. Then you try to make a program, usually a computer program, that will do some good things for you, like, for example, recognize your voice or do the web search for you. So machine learning is a big area, and deep learning is actually a sub-area in machine learning. And then the question is, so what deep learning mean? So people may have different views, but usually in the society, people use deep learning refer to the series of machine learning models that based on deep neural networks. So Professor Jeff Hinton established the term deep learning in 2006 and have created this deep multi-layer nonlinear layer deep neural network. And later he worked with Li Deng and UWEE and many other colleagues and obtained the first breakthrough in deep learning speech recognition. And this is one of their publications, which is quite popular. But the question is that what deep learning actually can bring to us? Well, so think of the universal translator. So people have dreamed of this kind of translator for a long time. But unfortunately, there are errors in speech recognition, and let alone how to translate those errors to another language. So with deep learning, actually, because deep learning technology can bring the speech recognition error to such a low level that translating from one speech to another language become possible. Actually, 2 years ago, we built a first real-time speech-to-speech translation system. And Rick Rachel actually gave a presentation and demo that system 2 years ago in China in front of 2,000 Chinese students. And on stage, Rick Rachel just speak naturally in his voice, in English, of course. Then our system will pick up his voice, recognize into text, then translate that text to Chinese, and speak out use a computer speaker in Chinese. So the student can actually receive his information correctly and seamlessly. Here, I'd like to show a little demo of that system. So we can see how accurate or how interesting that could be.
There's much work to be done in this area. 在这方面有很多工作要做。 But this technology is very promising.
用这个技术很有希望。
And we hope in a few years that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
Personally, I believe this is going to lead to a better world.
这我个人认为，这将导致更好的世界。
I hope you enjoyed the rest of the presentations today.
希望今天你喜欢其他的讲座。
Thank you.
谢谢。
So actually, I was at the conference at that time, and all the people, including me, actually are kind of like impressed by what Rick delivered. So it's a seamless demo, and after that, actually, people notice this breakthrough and start to catch up. And within, in last 2 years, actually, deep learning become a major new technology, actually totally shifted the paradigm of speech recognition. And many major players in this field pick up this technology and quickly deploy it to their products. Nowadays, we can see all the speech products for example, in Apple, in Microsoft, in Google, and even companies in Baidu, in Xingfei, they all use this technology and dramatically reduce the speech recognition error rate, which enables a lot of other applications. So this is actually the model I copied from the paper from our colleague 2 years ago. They developed for speech recognition using deep neural network. And here is the progress we can see. Almost after 10 years of no major improvements in the speech recognition field, suddenly, with this deep neural network-based speech recognition system, MSR actually reduced the error rate from 23% to almost half to 13%. And actually, we further bring that error rate down to single digit for Rick Rashid's demo. This basically shows how fast or how dramatic this new technology changed the speech recognition field. So not only in speech, people also see great improvements in image objective recognition using deep neural network. So almost about more than 10 years ago, Professor Yang LaQuan developed this convolutional neural network originally proposed for the image processing or image recognition. It's a multi-layer neural network model. Unfortunately, at that time, because the limitation of the computer power, and the other facilities, it didn't really fly. But here is a good illustration how that model works. Given an image, then you build a small convolution nets, which actually works like a filter, and scan over the whole image. Then after the scan, it gets an abstract feature map. And then after pruning, it gets a more high-level feature map of this image, which captures the major information in this image. And so in the early stage, people use some shallow model to do this image recognition. For example, given you an image, you tell what it is. For example, the previous image is a parrot. But then after 2012, there is also a paradigm shift in image object recognition field. People start to use this multi-layer, highly connected nonlinear models, which are deep neural networks, to do image recognition. And this also brings in great progress in terms of reduce the recognition error rate. This ImageNet is a benchmark in the society. The task is that give you an image, you tell which category it belongs to, and there are total about 1,000 categories. So before 2012, people used this traditional shallow model. And in 2012, the Toronto group, led by Jeff Hinton, they implement actually much scale up the convolution nets I just described 2 slides ago. And then they apply to on this task. And dramatically, this model cut the error rate by almost half. And that's not the end. Over the last 2 years, from 2012 to 2014, the error rate is cut by another half, because more and more people are convinced by this method and spend most of the energy and spend all the resource to keep improving, scale up this model, and we keep seeing the dramatic improvements on image recognition field. So basically, in 2-3 years, the error rate is cut to only a quarter. So people have shown this great success in speech and image by applying deep learning technologies. So even the media actually get excited. So they all think probably we're reaching the new stage, and that's the ultimate goal. But how about natural language? So neural network has also been applied to many natural language tasks. About 10 years ago, Professor Joshua Bengio had proposed this neural network-based language model. By language model, people basically want to predict the next words, given the past history. For example, you want to predict the words chases, given the past 2 words, the cat. So given cat is like a kitty, so it's probably chase a lot, so it's high probability. And in contrast, the cat cannot speak, so the probability of have a word says after the cat is very low probability. So the neural network language model is built to predict these events. And more recently, Thomas Mikloff have developed the recurrent neural network-based language model, which bring the error of the language model to a lower level. And the people have also tried the deep learning for spoken language understanding. Like people use smartphone nowadays. So you can talk to a smartphone, and the smartphone try to understand what you are saying and fulfill your request. So there are 2 major scenarios. You want to detect the domain of your request, and also what's the semantic slot in your request. For example, if you talk to your phone, say, show me flights from Boston to New York today, suppose the program will first detect it's a travel domain, and you are looking for flights. And then the actual information is about the flights from Boston and to New York, and the date is today. So we have developed a series of deep static neural network model try to solve this issue. First, we try to solve this domain classification problem by stack a series of 3-layer regular neural network to form a deep neural network model. This actually works extremely well. Compared to a standard baseline, which is a boosting-based method, we can reduce the error rate from 8.5% to less than 6%. So this almost reduces 1/3 of the errors. And we also can see that the error keep going down when you get more and more layers stacked up to 6 layers. So this demonstrates deep learning works well for domain classification. And also we apply this for deep learning technology to a semantic slot filling task. For example, if you talk to a computer, show me flights from Boston to New York, you want to identify Boston is the keywords you want to pick. New York is another keyword, and today is the time you want to pick. So we have developed some recurrent neural network to tag the semantic meaning of each word. And we test on some tasks like the airline booking system. And we show that compared to traditional method, this can also reduce the error rate dramatically. So this also shows a great success. But is that the story for the whole natural language processing? Probably not, because all this task is basically try to classify your input to some category. But now actually, understanding human language is more challenging than that. So why understanding language is difficult? Because we know there's a great variability in your language. That means different people will express the same concept in very different ways. There are also great ambiguity in your language. When you say something, probably it can mean many different concepts. You have to understand a lot of context to really understand what that means. And something which express so very similar to each other could mean something totally different. For New York City and the New York Times, one is a city location, another could be just the newswire. So, and also the meaning of a text usually is very vague and latent. This is unlike the speech or the image recognition task. In speech or image recognition, you know what exactly you want to produce, the word or the category. But it is not easy to write down or clearly express what exactly the meaning is given a text. Even for human, it's difficult. So learning semantic meaning of text is basically a fundamental challenge in natural language processing. And we'll spend probably the next 20 minutes talk about that. So in terms of learning semantic meaning of text, I'd like to introduce a concept called semantic embedding. The idea is that we want to project this raw text into a continuous semantic space. So we can compare the distance of two texts. We can measure the relationship of two texts. Then it's much easier to understand the text than just look at raw text. The concept can trace back to the LSA task, LSA program in probably 20 years, more than 20 years ago. So for each word, we want to capture the word meaning, project it to be in a semantic space. For example, the word usually is represented as a symbol or an ID in a huge vocabulary. For example, the word cat itself don't have any meaning. It's just an ID in a big vocabulary. Then by word embedding, we actually want to project this word to a lower dimension continuous valued vector, which have some semantic meaning there. And eventually, we want to construct such a semantic space. And each word, each term, each text could be just a point in this space. And then we can easily measure the distance between two words. Like cat and catty, they're supposed to be very close in this space, and we know they probably mean similar things. And the catty and Porter and Seattle is close to each other, but they are both far away from cat and catties. So this actually will bring a lot of benefit for the image, for language processing. What's wrong with this? So people have developed many different methods to learn this kind of embedding. One of the early work is conducted by Dr. Colloquium and his colleagues. In this case, he tried to first map every word to a low dimension vector, which is the embedding we're talking about. Then he concatenated these 5 words embedding together and convert to another hidden layers. And eventually get a regression score from this hidden layer. And the training is also very interesting and inspirational. He basically says there are good 5 grams. For example, you can just go to a regular textbook, you get any 5 words consecutive, it's treated as a good one. Then you can replace the middle words to any other random word. Then you think this one is called a negative sample. Then he trained the whole model such that the score of the good 5 gram shall have a score higher than the score of the negative samples. By keep reading a lot of this data and train this model, eventually the model will learn semantic embedding for each word. So following this work, there's many other works also do the same job. For example, a byproduct of this recurrent network language model I mentioned before is also can be viewed as a word embedding, because in the first layer of this language model is a big matrix, and each word will correspond to a column in this matrix, and it can be viewed as word embedding. And there's some other works recently. And more recently, we actually revisited the word embedding concept. I mean, given a big word embedding matrix, it's quite a neat concept. For any word, you just look up this big word embedding matrix. In this matrix, every word have a vector in the semantic space. Then you retrieve the vector and represent this word by this new vector. And the only problem is that sometimes in a real world, the vocabulary could be large enough that you don't want to build an individual vector for every single word. For example, in the modern commercial search engine, you may see probably up to 100 million unique tokens in your query log. And people just input anything in the search engine, and there are a lot of spelling errors, a lot of typos. So it's just difficult to just build one vector for every single word. So a more decomposable, robust representation is preferred. So we try to propose build semantic embedding on top of sub-word units. By doing this, actually, we decompose a word into a sub-word units, and then reduce the problem from modeling almost unbounded variability like word to a bounded variability like sub-word. Here is an illustration. In the traditional way, if you're supposed to have 100 meaning unique tokens in your vocabulary, and you want to build a 500 dimension semantic space, then you end up with build a word embedding matrix like 500 times 100 meaning 3 parameters. And what we do is we will try to decompose this W to 2 matrices, and like this. The first layer, which converts the raw word to the representation by the sub-word unit, which we call SW encoding matrix. Then we only need to learn SW embedding matrix, which have much smaller size. By doing this, we basically decouple building the semantic space from the raw size of the vocabulary. And then we can support extremely large vocabulary. And there are many ideas how to pick up this sub-word unit. You can use letters, context-dependent letters. You can even use phonemes, which you can describe the pronunciation property of this word, and many others like morphologies. So here's a simple example show how to go from the sub-word unit vector to word vector. For example, suppose we use context-dependent letter as our sub-word unit. So each unit is actually a letter trigram. Then for each word, like cat, we can decompose the cat to be a sequence of these tri-letters. And in training, we suppose to learn a matrix. In this matrix, for every tri-letter, we will learn our vector representation. Then for actual word cat, we first break it to be the letter trigram and look up the table, and then retrieve the corresponding vectors and merge them to form the word representation. So even further, going beyond, we want to estimate the semantic embedding not only for word, but more for the phrase or sentence level, because we know the meaning of a word is very ambiguous. You have to consider the context and to really understand what does it mean. So build a semantic meaning for phrase or sentence make more sense. So here is a general architecture of applying deep learning to learn this semantic embedding for text. The input is just a raw text like a sentence or sequence of word. Then you go through a sequence of nonlinear layers. After each layer, the information is transformed, and then the deeper invariants of the concept embedded in the text are extracted. And eventually, you will reach to the semantic space which have the abstract representation of this word. So the problem of this model is that the semantic meaning of text usually shall be learned for the model. It's very vague and latent. There's no clear target for the model to learn, because people cannot just specify what exactly the vector value shall be for any arbitrary text. It's just in a latent space. So without this signal, it's not easy to do this backpropagation training for neural network. So fortunately, although people cannot specify the latent semantic values directly, people usually know if two texts are similar or not. And that's actually become the training signal for us. So we recently developed a series of so-called deep structure semantic model, or sometimes referred to deep semantic similarity model, which actually try to learn the semantic meaning for a sentence or for a phrase. So it's scalable, and it's trained by a similarity-driven objective. And this model is also trained using signals that sometimes without any human labeling effort. For example, we can just use this, the user log in the system to train the model. And I will show the power of these models. So here is a quick illustration how this model works. So for example, in the initialization, we randomly initialize the neural network weights. Then given our input text strings, you go through the sequence of the nonlinear transformations and get the semantic vector of this text for racing car. You do the same thing for other texts, for example. And at this moment, this vector didn't make any sense because the whole neural network is randomly initialized without any training yet. But we know the word racing car actually is close to Formula 1 in the human concept. And we know racing car is totally different from the meaning of racing to me. So based on this signal, we can train this model. The model is trained in such a way. For example, we first compute the cosine similarity between these semantic vectors. And then we try to move the model such that the vector of the racing car and the vector of Formula 1 shall be close to each other. I mean, the actual place is not important, but we just want to make them close to each other in the semantic space. And on the other hand, we want to make the semantic representation vector in the space of the racing car and the racing to me far away from each other. By collecting these statistics, we can get the training signal, and we backpropagate this training signal to train the whole model. And after training, we hope the model is able to tell that racing car and the Formula 1 actually have two vectors very close to each other in the semantic space. And then we know they actually mean a similar thing, and they are talking about the same semantic meaning, this concept. And for other words, text like racing to me, although it has some word overlap with a racing car, actually the model shall be able to tell they actually point to very different locations in the semantic space, and we know they're far apart. So here are some formal definition of the training of the models. There are two major steps as in usual machine translation step. First, the data. To train such a model, we need to prepare the semantically similar text pairs. And I will talk a little bit later how we prepare these data. And another is the learning the objective. Basically, we want to compute the content similarity between different vectors. And based on if they are similar or not, we adjust the model. So we also develop some other advanced model, for example, to capture more information. In this model, we try to capture the sequential structure in the text. And we also try to identify keywords or concepts in the text. I'd like to illustrate a little bit about how this model works. For example, given a sentence like automatic body repair cost calculator software, as actually this is one of the common queries people search in Bing. And what does it mean? We first build a sliding window, just motivated by the convolution filter. We build another text filter, just sliding over the whole sentence. And for each term or each phrase in this sentence, we try to construct or learn a semantic feature, represent the intent or semantic topic in this 3 words frame or 3 words terms. Then we combine this local individual features to be a global semantic intent feature, and eventually project this to the semantic space. And so I'd like to dive in a little bit more, show what we learn actually in this model. So in the first layer, in the convolution layer, we try to map every short phrase to a meaningful semantic vector. In here, for example, we'll learn a 500-dimension vector for the 3 words auto for the word body, given the context auto and the repair. So we know the word body is ambiguous. This means many different things. Within the context auto repair, we're pretty sure this body is mean the car body. And so in the semantic space, actually we can see those bodies are close to other bodies referred to car body. It's called a car body shop or auto body parts. And we also can see for other bodies, although they are the same body, actually they mean like human body. So actually in the semantic space, they are far apart from each other. So this is our quantitative evaluation. For example, we compare the distance of different bodies within different contexts to the car body shop phrase. And we see that for the first 3 example, car body case or something like that, it's very close to the car body shop in terms of the cosine similarity. And other bodies talk about the human body actually are far away. We also want to dive into the max pooling layer to see what does that mean or what we learn here. By merging the different local phrase meaning feature to a global meaning, actually we are able to capture the most salient concept embedded in a whole sentence. For example, in this auto body repair cost calculator software sentence, actually the true or most important concept is people want to find a calculator to measure probably his loss on auto body repair. By doing this model, the words that have the most significant topic will win in this max pooling operation, in this max pooling operations, and will survive. And we can trace back which word win at which location and how much they win. And by calculating that, we know, okay, these 4 words are most significant words in this sentence. And actually, this model is capable to do very complex semantic matching. Here is a little complicated story, but it's also very interesting. This is a very common, this is not a very common disease. It's basically sarcoidosis. It's a disease with a symptom that you have excessive amount of colloquium in the urine or in the blood. So we need to avoid any medicine that increase the absorbing of colloquium. On the other hand, we as humans know that vitamin D is very closely associated to colloquium absorbing. So as human, we know this disease is associated with vitamin D, which will eventually associate with the colloquium absorbing. But how the machine can learn from that? Actually, when we dive into the model, we found the machine actually is smart enough. They can, in this sentence, the machine, the DSSM, will activate these 3 nodes. This is a neural in the network, in neural network. As this words and this word and these 3 words activate these 3 neurons. And by doing like this, by just look at this, we don't still understand what these 3 neurons mean in the semantic space. Then we look at another sentence. In this sentence, we found actually this disease itself directly also activate these 3 neurons. That means the machine is able to is capable and learn that this disease and these 3 terms actually mean the similar thing, although it's latent in a semantic space. And they're going to match these 2 semantic intents. And there are more. So given this model, we are able to apply this model to many different important natural language applications. We actually apply this model to a series of applications like web search, ad selection, entity ranking, recommendation, machine translation, and so on. So limited by time, I'm not going to go through all of them. I will just pick a few interesting applications and show how this model can help. So first, back to the basic question, how we learn the word's meaning. So as people said, you should know a word by look at the company its caps. So we can learn the word meaning by construct this semantic similarity pair, because we are shown the semantic meaning of a word is similar to the context around this word. So for each 5 words in sequence in a big body textbook, for example, you'll pick the middle word, treat it as a single word, and put it at the right-hand side in the model, and put the surrounding words as context of this word at the right-hand side and the left-hand side. And then you train the model to make sure the meaning or the semantic vector of this word is close to the semantic vector of its context. By using this simple information without any human supervision, you can train the model. And we actually perform these experiments on about 1 billion words of Wikipedia data set. And we learn the semantic vector for every word in a 600K vocabulary. And for each word, we will produce or project it to a 300-dimension semantic space. So, well, after all the training, we end up with this nice semantic space. So it's so nice, so we have to dive in to look at details. So for example, we dive into this cloud. And we found actually all the words about months actually collapse and cluster together in this small cloud. We also look at other examples. For example, this this cloud actually corresponding to all these nation names. And this cloud actually corresponding to the name of states in US. And remember, all these properties are learned automatically just from a big body of plain text from Wikipedia. Everybody can get access to that. And there are more. For example, this cloud talk about sports, games, and champagne. So we can even perform some simple semantic reasoning task given this learned semantic space. For example, if you ask which word are semantically close to this first column words, for each word in the first column, we first project the word to a semantic space given the model. Then we look around in that local location and see which other points are close to this particular location and get them out and sort by distance. And then we found the top words close to this king are all for people that have power and authority. And for people, for the word woman, you get all the people, all the words like close to woman, I mean person or girl or man. Or for words like France, the name of the nation, you get other, actually you get other nation's name show up, which close to the France. Even more, we can perform some more interesting tasks given this semantic space. For example, sometimes when we take the exam, you can see, okay, people may ask, you will say, given summer have a lot of rain, so what do you have in winter? So all this question or analogical question actually can be computed just like an algebra operation in this semantic space. For example, we just get the vector of all these words. And then we subtract vector 1 from this vector 3 and plus the vector of word 2. And then we get a new vector in the semantic space. Then we look around in the space, just around this point in the semantic space, and check what other words in that location. And thus get them out and sort it by the distance. And we actually get snow for winter. And meanwhile, if you see, if Italy has Rome, or which city is to France, just like Rome to Italy, actually we get Paris. And even for some more open-ended questions, like if I is a part of man, so you get a motor, which is a part of car, and so on and so on. So this basically say, by learning from a big body of text without any human annotation or any human supervision, and you can still get a lot of sense and learn the meaning of the text reasonably well. So now let's talk about a more practical or serious task, web search, which actually makes billions of dollars, like for Google or for Microsoft Bing. So in web search, people input a lot of queries, and then look at the documents, click at a document, which usually fulfill their request in terms of the query intent. Then we can automatically mine a lot of this query to document similarity, the semantic similar text pairs, because we kind of like assume if people input a query and click some documents, then there must be some semantic similarity between the document clicked and the query the user input. So by looking at all these search logs, we get a lot of this semantic similarity pairs constructed by query and the title of documents. In this case, we just use the title because we say title is the most significant and informational part in the documents. So by mining a lot of these data, actually in these experiments, we mine like 18 million query document pairs. Then we can learn such a deep semantic similarity model, which can tell the intent of the query or the topic of the document. And then later in testing, when a new user come in and type in a new query, we can get the abstract intent of this query, and then search over all the documents which match this query intent, and return back the documents to the user. So in a more scientific evaluation on a benchmark, we compare this model to many other models, like topic model, or latent semantics analysis model, or lexicon model. And we see a big breakthrough in terms of the NDCG, which is a quality measurement of the search quality. So this model can also be applied to many other tasks like machine translation. The concept is quite simple. Machine translation itself is a very complicated system, so I don't think I have enough time to describe the whole machine translation system. But applying DSSM to machine translation is a little actually is intuitive. We just try to map the phrase in the source language or in the target language, both of them, into a same language-independent semantic space. Because we know it doesn't matter you speak English, French, or Chinese, you pretty much mean the same thing. And then if we project all these different languages to a same language-independent semantic space, it's much easier to measure the translation quality or translation relationship between two different phrases. So by applying this model to translation, we are able to also improve the translation quality on some major benchmark. I see one blue point, which is significant in the machine translation evaluation. So another task I'm going to talk about is so-called question answering. This can be viewed as an extension of the search engine people use every day. So now in search engine, usually you just type in a query, and you hope to get a bunch of documents, and you just check them one by one. In question answering, the question is treated as more complicated semantic and have a strong semantic structure. Then you actually want to parse the semantics in the question. And then you look through a knowledge base, which contains all the knowledges. Then you do some inference in the knowledge base and directly return the answer. For example, if you ask who is Justin Bieber's sister, you directly go back to the name of the sister, not just give you a big page. So why question answering is difficult? One challenge, just like many other NLP tasks, is there are a lot of ways to speak the same question. So there are so many variations, but you shall be able to tell, the machine program shall be able to tell, they actually ask for the same question. So DSSM actually can perform this matching, the intermatching for question answering well. For example, giving you a question like when or DVD players is invented, so you can first pass this question to two parts. One is we call the pattern of the question. Another is we call the dimension of the entities in the question. Suppose you get this one. For example, the pattern is when or M invented. Actually, the M can be anything. It could be DVD player, it could be car, it could be computer. Another part is the mention. The mention is a specific entity mentioned in these questions, like DVD player here. And of course, mention can also be many other things. And meanwhile, you look at the knowledge base. In the knowledge base, all the knowledge are organized in a relationship entity 1, entity 2 form. Basically tell what's the relationship between two entities. Then you actually can build a small space. It could be a generalized semantic space we call it relation space. In this space, you project the pattern, which is mentioned in raw words, and the relation in the knowledge base to the same space and measure the distance of these two match in an abstract space. And do the same thing for the mention. So you can map the mention to the actual entity name in the knowledge base. So in this case, the matching of the mention probably looks trivial because DVD player just directly go DVD player. But the image that actually people can see a lot of different way in terms of DVD. You can just say DVD or other players. Yeah. So after this match, you can retrieve the answer, which is 1993 for this question. So you go through and compute the most likely answers and search the most likely semantic parsing operations, and eventually give you the best answer here. So we conduct some experiments on question answering benchmark. Actually, the data come from UWEE, from the computer science department. They construct this database, and we train the deep semantic model on this database. And then we evaluate on the benchmark test set. So the question answering task is evaluated in such a way. You want to answer as much as possible questions, but also you want to answer them as accurate as possible. So recall, the x-axis is a recall, means how many questions you answered. You can choose don't answer any question, so you don't give wrong answer. And the y-axis is the accuracy of your answer. So basically you want to higher recall and higher precision. And basically, the curve, the higher the better. So from here, evaluation, we can tell actually the red curve is based on the DSSM, which significantly outperform a traditional model, which is based on lex matching and translation matching. So we just talk about a lot of pure natural language tasks. And at the end of the talk, I also want to mention some other latest interesting work, which we can go beyond text. Actually, this model can used for multimodal learning, because not only text have meaning, even every image, every picture also have some semantic meaning embedded. And it is possible that we can map the image to the same semantic space with the text. And this actually brings a lot of implications. For example, you can always attach a description given any image you captured with your smartphone, for example. Or you can do product search given an image taken about a particular product. So actually, with this technology, as Microsoft, we build an automatic caption generation system for images. The flow is going like this way. Suppose the input is an image like this one, like big stop sign on the street. First, the deep convolution net I just described before is used to extract a lot of attributes about this picture. Like there's street, there's signs, and many other things. Probably there's some noise here as well. Then we put this bunch of attributes through a language model and generate a list of possible sentences describe this scenario, this sense. Then we apply this cross-modality image text joint DSSM to rank this generated sentence against the original image and pick the most likely one and output it. So eventually, for this particular image, we will generate this sentence. So we actually want to evaluate this system against the human performance. This evaluation is also interesting. For a lot of testing images, we first hire 5 annotators. Each of them will provide an annotation, just like a caption for each image. Then we hold one human as like a control system. And the other 4 humans just like a reference provider. So for each image, we have 4 golden reference provided by the first 4 annotator. And we hold the 5th annotator as a control system, pretended as a control system. Then we have another judger come in. And every time we give the judger an image and 2 sentences. One is come from the 5th person annotator. Another comes from the system. Then we ask the human to see which one the judger prefer to. And these are evaluations results. So blue score is an automatic metric to estimate the quality of the generated sentence. And in terms of blue score, actually the machine can catch up with human almost no gap, actually a little better. And even for human judger, actually about a little less than 20% of time, the human judger actually prefer the machine output than the other humans annotation. This is quite actually encouraging, thinking that how far human used to go beyond a stupid machine. And here are some good examples I'd like to share with you what human generate and what machine generate. For example, this is a picture, and the top one, the top caption is generated by the machine. Given this picture, and the machine will generate like a kitchen with wooden cabinets and a sink, where the human side are oriented kitchen in designed with rustic wooden parts. So they're close. Actually, if I'm the judge, I would probably prefer the machine outputs. And there's another one. So the top one is generated by the machine. Basically, given this picture, the machine said a woman in a kitchen preparing food, where the human annotator will see a woman walking on a counter near a kitchen sink preparing a meal. A little of both, but pretty much the right thing. And there are more examples, like a bicycle. The machine is able to tell this is a bicycle, and also can tell there's actually a river in the behind. and then come up with a reasonable sentence like a bicycle is parking next to a river. And the more like people, the machine can recognize there's a clock tower in the middle of the street. And there's another picture, the machine can tell a group of motorcycles parked next to a motorcycle. Where the humans speak a lot, probably the focus is a little different. Yeah. And there's another one. So machine said, okay, a man holding a tennis racket on a tennis court. So the machine not only be able to tell there's a human, but also be able to tell the man is holding a tennis racket and also on a tennis court. So all this show there's a good promise that we can use deep learning to understand different semantic meanings and associate them together and facilitate and enable a lot of new exciting scenarios. So there are many other random work on deep learning in natural language processing. So like long-term, long-short memory, recurrent network, recursive network, and other tensor product representations. So limited by time, I'm not able to go through all of them. So now let's just summarize the talk. So basically, we see there are great progress in deep learning, and we witness major breakthroughs in speech, in image, and in language. And we also see exciting advances in learning continuous semantic spaces. Not only the continuous semantic space actually can lead to superior performance for a range of natural language tasks like translation, search. And even more, we can actually learn both image and text together and in a joint semantic space. Just like this space, we can embed all these words as well as relevant pictures all together in a unified space, which will facilitate a lot of new exciting cross-modality scenarios. And look forward, we hope we are able to build a universal semantic space for all modalities, speech, vision, text, social graph. And we also want to build a universal intelligence space too, so we can do reasoning, do this knowledge inference in the continuous space. And hopefully the model is able to acquire the intelligence from the ambient signals automatically without any supervision. As we show in the beginning, the sense of the word can be learned automatically from Wikipedia, or the search intent, the query intent, document intent can be learned automatically from the user query log without any human effort to annotate them. And now it's also a good time for deep learning, given the big data actually coming in and also the big computation. Think about just a few years ago, when you talk about a big computation, you think of a big computer cluster, have probably a big room or a lot of computers. But nowadays, actually, you can just buy one computer, use GPU, and which have 10,000 computing cores, and which can learn a billion sentences just in one day. So it's just a start, and I think a more exciting future just ahead. So that's pretty much conclude my talk, and thanks.
Okay, given the time constraint, do we have some 2 or 3 quick questions? Yes.
So I have 2 questions. First one is that in your deep structure semantic model, did you use the layer-wise answer question pre-training before the sequence training? The second one is that in your multimodal learning, how did you combine, or how did you tackle the issue that the original space of the, for example, the image and the text, is wholly different. So how did you?
Okay, that's a good question. So the first question is about, do we do any pre-training when we build this deep semantic model? Another question is how we map image and text to a same unified space because their input is so different. So for the, I can tell probably you have some experience in deep learning before. So for the first question, in our case, we found, and many other groups also found, pre-training is not necessary if you have a lot of data. So even in speech, in image, and for us in text, we found that it's not necessary. You just do some random initialization and just train it. And given the powerful machine, as I said, you have 10,000 cores in one machine, so you actually can afford train a model much bigger and use much more data than before. For a second question, in our case, So yes, the raw input of image and text is very, very different. So for the image part, we first go through a regular image convolutional net, and up to some level. So look at the first level. In a traditional image net, your input is raw pixels, and you go through all these nonlinear layers, and eventually you will output the category of this image. But in our model, we drop this category layer. We only keep the last two of one layer, which we think which is rich enough to capture the semantic meaning or all the information in the image, but also abstract enough so we can fit this feature to the DSSM. So in training, for example, think of if you go to the image search engine, you type in a text query, and you click some images. Then we know there are some association between your query and the image. And the image will go through this net and get the vector. And the query you import becomes the semantic similar pair of that image. Then we can train a regular DSSM. And in this case, for example, if we import a parrot that tricycle, hopefully we'll come this picture back later. Yeah.
One more question? No? Okay. Before we thank our speaker today, I'd like to also make an announcement. Next week, our colloquium speaker, Professor Paraj from Stanford University, he is also going to give a very tutorial type of talk about all this wireless access technology in the past 20 or 30 years on Monday afternoon, 3:30 in room 125. So in case you are also available to attend that talk, it's a very wonderful talk. This is a part of our LITO lecture, distinguished LITO lecture series. Okay, so without further question, let's give a big hand to our speaker today.
Thank you.